You probably remember trigonometry from high school math class, right? Well, what if I told you that same math is being used, like right now, to save lives in emergency rooms? Today, we are going to unpack the seriously hidden connection between a simple circle and the super complex world of medical imaging. Okay, let's dive right in.
It kind of sounds like a riddle, doesn't it? On one hand, you've got your angles, circles, sines, and cosines, and on the other, you have doctors literally racing against the clock to see inside a patient's brain. Well, the link is all about translating the messy, chaotic signals of the human body into a language we can actually understand, and that's the language of waves.
So to really get this connection, we first need to crack a kind of secret code, and it's a code that's hidden inside a simple circle. The key to that code? It's a tool you might remember called the unit circle. Now, the unit circle is just beautifully simple. It's nothing more than a circle with a radius of 1. That's it. But its real power is in that simplicity. I want you to think of it like a perfect map, where every single point along its edge tells a unique story.
So how do we build this map? Well, we start with the easy stuff, the cardinal points, 0, 90, 180 degrees, and so on. Then we slice the circle up into 45-degree angles, then we fill in the 30 and 60-degree angles. And just like that, the whole circle is filled with these key points, and every single one has its own unique angle and its own coordinate address.
And here it is. This is the secret code. For any angle you pick on that circle, the cosine is just the x-coordinate, and the sine, that's the y-coordinate. It's that simple. This shows they're not just some abstract functions. They are the literal, physical address of a point on this map.
Okay, so that's great. We can find coordinates if we know the angle. But what if we need to do it the other way around? This leads us to our next big challenge. This is the crucial question, really. Think about it. If a doctor gets a signal from a machine, just a single data point, can they work backward to figure out what biological event caused it? To do that, we need what are called inverse functions.
But there's a catch. See, the sine function is a wave, and it goes on repeating forever and ever. So if you pick a value, let's say 0.5 on the vertical axis, and you look across, you'll see it hits the wave in an infinite number of different spots. That means we have way too many answers for a single question.
So how do mathematicians deal with this? Well, they basically cheat. They just impose a rule. They decide to only look at one small piece of the wave, a section where every y value matches up with only one x value. So by restricting our view from negative pi over 2 to pi over 2, we guarantee we get one unique answer every single time.
And that unique answer comes from a new function, the arcsin. It's literally designed to do just one thing: take a coordinate value and give you back a single definite angle. So problem solved. All right, so we have our codes for going forwards and backwards, but right now everything's pretty static, like a snapshot in time. To make this stuff useful in the real world, where things are constantly in motion, we need to bring in the idea of change itself, and that means calculus.
The whole point of calculus, specifically derivatives, is to measure how fast something is changing at a very precise moment. For our sine waves, it's like asking, what's the steepness, the slope, at any single point? This is exactly how we can analyze dynamic systems, like blood flowing through the brain.
Now, don't worry, we're not going to get into the nitty-gritty proofs here, but these are the powerful tools that calculus gives us. These formulas tell us the precise rate of change for our inverse trig functions, and these are the mathematical engines that are going to power our final step. So, let's recap. We've built the unit circle, we've figured out the problem of inverses, and we've unlocked the power of calculus. Now let's see how all these pieces come together in a hospital ER to actually save people's lives. When a patient is having a stroke, every single second counts. Doctors need images, and they need them fast. There's a type of scanner called a flat detector CT, or FDCT, and it's right there in the operating room, which is a huge, huge advantage. The problem? These machines produce data that's, well, it's messy, it's noisy, and that makes diagnosing the problem much harder and slower. To fix this, researchers came up with something called the time separation technique. Now, instead of just trying to clean up a messy picture, it actually rebuilds the picture from the ground up using a mathematical model. It basically assumes the messy signal is just a mix of a few simple, clean signals. So what are these simple, clean signals that they use? Well, this quote from the research paper, it reveals everything. They modeled the incredibly complex signal of blood flowing through the brain as just a combination of basic sine and cosine waves, the exact same functions we got from our unit circle. And does it work? Oh yeah, absolutely. By using this trig model to reconstruct the brain scan data, researchers saw a 6.6% improvement in the accuracy of their blood flow maps. Now, 6.6% might not sound like a huge number, but in a stroke situation, believe me, that extra bit of precision can be the difference between a good outcome and a very bad one.
What you're looking at here are perfusion maps. They show doctors exactly where blood is flowing in the brain, and maybe more importantly, where it isn't. And being able to generate these clear images from noisy data and doing it fast is all made possible by using the elegant language of circles and waves to describe complex biology.
So there you have it, from a simple circle with a radius of 1, all the way to a life-saving algorithm used to diagnose a stroke. It really makes you wonder, doesn't it? What other world-changing secrets are just sitting there, waiting to be discovered, inside the pages of our old high school textbooks?